students. Today we are going to talk about section 12.2, and this is your last statistics lesson of the semester. This is it. We are going to talk today about tests for independence and the homogeneity of proportions. This is going to be a lot like the last lesson. So we're going to be doing a chi-square test, but here we're going to be doing a chi-square test for independence to determine if there's an association between a row variable and a column variable in a contingency table. So like the last lesson, we're still talking about categorical data, but unlike the last lesson, we have more than one variable that we are considering. So our null hypothesis is that the two variables are not associated, or that they are independent of each other. And the alternative is that they are associated, or that they are dependent upon each other. So just again, and it's the same hypotheses every time, so that makes it nice. You don't really have to put a lot of thought into it. It's either null hypothesis, they're independent, unrelated, or alternative, they are not independent, they are dependent, they are related to each other. So the idea behind this type of testing is to test the types of claims that compare actual counts that we would expect to find if the null hypothesis were true. If the two variables are independent of each other, what would we expect the counts to be? And then what are the counts, and let's compare. If two events are independent, this goes way back to chapter 5, I think, probability, and means multiply. So if two things are independent of each other, then the probability of one happening and the other one happening is to do a multiplication of the two probabilities. So in this example, if we have a poll of 883 males and 893 females, and they were asked if you could only have one of the following, which one would you pick? Money, health, or love? The responses are presented in the table below, determining the expected counts within each cell, assuming that gender and the response are independent of each other. So the idea of expected responses, we want to first look at the row and the column totals. So it told us that there were 883 men and 893 women. So those totals were given to us in the problem. The other totals we would want to just add up to get what those totals are. Then we could figure out what is the relative frequency of each of those. We would divide the total for the row or the column by the total for the table. So the total for money, for example, was 128, and the total for the table was 1,776 people were involved in this survey. So that means 7%, 7.21% of all respondents, whether men or women, answered money to this question, right? Or on the other side, there were 883 men out of the 1,776 people involved in this study. Divide that out, 49.72% of the respondents in this survey were men. So just about half men and half women. So after we do that, we can then figure out what percent would we expect to happen in each of the individual cells. So for men and money, we would take the 0.0721 of money times the percent of men, 4972, and when we multiply those together, I get 0.03584812 on my calculator, so just round it off to 0.0358. So by doing the multiplication of the row and the column percents, it gives us what percent we would expect to find within each of these. And then if we multiply that percent by the number of people involved in the study, that would tell us how many people we would expect to fit into each of those categories. So in the survey, we would have expected about 64 men to choose money. likewise 64 women to choose money. We would have expected 507 men to choose health, etc. So these are what we would have expected if gender and choice is independent of each other. Okay. So as a kind of a summary, we could do our row total times our column total divided by the table total. Then we're going to do a chi-square test on this. So to do our chi-square test, we are going to calculate that chi-square statistic that we talked about in the last lesson, where we do our observed, how many actually answered each of them, minus the expected, what did we expect for each of them, square it, and divide by the expected. Our chi-square distribution is R minus 1 times C minus 1 degrees of freedom, where R is the number of rows and C is the number of columns. So how many rows, how many columns? So in this problem, there were 2 rows and 3 columns. Men and women, was it money, health, and love? So 2 minus 1 is 1, 3 minus 1 is 2. So then multiply those together, and that gives you your degrees of freedom. We had the same requirements as we did in the last lesson, that all of the expected frequencies must be greater than or equal to 1. We have to expect somebody to answer in each of the categories. And we can have no more than 20% of them be less than 5. So our null hypothesis is that the variables are independent of each other, and the alternative is that they are dependent on each other. We choose our alpha level, make sure that we have met those requirements for the expected counts. Calculate chi-square, we're going to use technology to do that. And determine our critical value or our p-value. And decide, do we reject or not reject, and state that conclusion. So let's look at how to do that in StatCrunch. So drag myself back down to the bottom here. Okay, so I put the data into StatCrunch here. Now to do this, yesterday, to do our chi-square test, we were doing a goodness of fit. We were checking one variable according to what we thought the pattern should be. Now, that is not what we're doing here. Now we're trying to see, do these 2 variables depend upon each other? So for that, we are going to go to tables, and we are going to choose contingency tables. We've actually done contingency tables earlier this year, way back. I think it was like chapter 3, maybe, where we talked about categorical variables, and we talked about those row percents and column percents, and we talked about Simpson's paradox, where we have this seeming reversal happen, where like we talked about the examples where it looks like this hospital has a higher death rate, so we probably don't want to go there. However, once we brought in another variable of maybe the seriousness of the patients who they're serving, then we realized they actually really are a very good hospital. So we've talked about these contingency tables before. That's where we're going to go. Stat tables, because we have a table of data here, and it's called a contingency table. What we have is a summary. Data would be like respondent number 1 is male and said health. Respondent number 2 is male and said money. That would be a lot in this case, 1,776 pieces of information. So what we have is a summary, how many fell into each category. So we choose that. Our column variables are the money, health, and love. And our row labels are in var 1, because that is in var 1, I just put the men and the women titles there. So these are our column, and then this is where our row variables are, the labels. So then within this, I'm going to choose expected count. I want them to calculate that expected count. So we walked through that example of how we could calculate those expected counts, but this can actually do it for you as well. So we'll look at how to do these expected counts. And then down here, what we're doing is a chi-square test for independence. It is defaulted to choose that, so I don't need to select that again. And I'm going to compute. And this is what our output looks like. So the output looks like the chart. So it has the 82, 446, 355. Those are the same numbers that were in the actual chart. It gives us all the totals. Okay, it goes ahead and calculates all those totals for us. And then in parentheses there, that's the expected count. So it tells us the kind of key up here. That's the expected count. So we would have expected 64 men, expected 64 women there, and we went through those and how those are calculated by the percents. But it does that calculation for us here. Now down here it gives us our chi-square value, 36.8. Now remember, this is not the same as standard deviations. It's not 36 standard deviations away. But it is pretty far out there because our p-value is basically 0. So no matter what alpha level I choose, this is smaller than that alpha level. So we conclude there is a dependency upon gender and kind of priority here in terms of money, health, or love. We have to decide in favor of the alternative hypothesis that there is sufficient evidence to conclude that gender and the response are dependent on each other. Okay? All right, hop back into our presentation here. So now to see what that relationship is, because the alternative just tells us there is a relationship, it doesn't tell us what the relationship is. There's a couple different ways that we can determine what that relationship is. One way is to look at a graph. So actually, I'll go back out of this. One way is to look at a graph. Another way is to look at what the difference is between the expected counts and the observed counts. So I'm actually going to bring those results back up if I can. Okay, so as we look at these, we would want to say like, well, where's the biggest difference between what we expected and what actually happened? So 312 to 355, that's a decent difference there, or 507 to 446. So we'd want to compare those differences here. There's a difference of 60. So we could look at where's the biggest difference between what we expected and what actually happened, and that could help us determine what is the relationship that's happening here in terms of preference. Also, a graph is a pictorial way to do that. For the graph, we're going to choose the chart, and I'm going to choose to chart by column. And then I'm going to say, here are the columns, and my row labels are in the var one. And then I prefer mine to be vertical, and I split them. You can play around with those settings and kind of see what you might prefer, but I prefer vertical and I prefer them split. So then we get this graph that's the same as the one in the PowerPoint there, and we can kind of look at, well, what is seemingly the priority. So it seems that women prefer health more, and it looks like men were higher on the money and love. So we could draw whatever conclusions we might want to, but beyond that is speculation as to why. That's more of a psychological study, sociological study than statistical study. The statistics can tell us there is a dependency. We can look at the graph and see what is preferred more or less, but why, that then gets into other areas, not statistics. All right. So we're going to look at one other example here in a chi-square test for homogeneity of proportions. That means we're testing to see whether different populations happen in the same proportion for a given characteristic. So the procedures are exactly the same. So it has a different name, but we're going to go through exactly the same process. And so in this example, I think I have this data put in here as well. Yep. Okay. So the following question was asked. to a random sample of individuals in 1992, 2002, and 2008, so some different years here. Would you tell me if you feel being a teacher is an occupation of very great prestige? The results are in the survey below. Okay, so what we want to do is see our opinions changing. So as we move through the years 92, 2002, and 2008, are the opinions changing in the question of being a teacher is an occupation of very great prestige? Okay, so we're going to test the claim that it's the same for each year at the 1% level. So remember, the null hypothesis is always unrelated. So it doesn't matter what year you ask this question, you're going to get the same answer. And then the alternative is that the opinions are changing, that it depends what year you ask this question, the answer that you will get. And we're testing at the 1% level. So we're being very confident of our results here. Okay, so the process is the same as the last. So we're testing the claim that all of these proportions are the same. And our alternative is at least one of them is different. Something changed at some point. So to do this test, same as the last, we're going to go into Stat. We're choosing Tables and Contingency Table with Summary. We select our columns, which are the years. Our rows are in the one that I didn't label. I'm going to have it find our expected counts for us. And then it's opted to do our chi-square test already, so I don't have to select that. And I'm going to compute. All right, so it gives me the expected counts here, how many I would have expected for each of these. And it gives us our chi-square here. It also gives you your degrees of freedom. Degrees of freedom are calculated there as well. So the chi-square is about 25. P-value pretty much 0, which means even at that 1% level that we were testing, we do have to conclude these are dependent. There is a difference in these proportions. Now, this doesn't tell us what that difference is. Like, are opinions getting better of teachers? Are opinions getting lower as teaching being a high prestige job? So it doesn't tell us what the difference is. It just tells us that there is significant evidence that there is a difference in the proportion who are answering yes. If we want to know what that difference is, then we might need to start doing that comparison of where are these values higher or lower than expected. So in 2008, more people answered yes than expected. In 2002, just a little bit more, but that's like almost right on. And here, fewer people answered yes than what was expected. So from that comparison of expected counts, it seems like in 2008, teaching was regarded with higher esteem than in 1992. Okay, so that's one way to look at it. Another way would be to look at one of those graphs. And again, if you want to graph, we're choosing a chart of columns, our column variables there, and our row labels. Again, you can play around with this. I prefer them to be vertical and split. And then, oops, compute that. And so then we can make that visual comparison. Our yeses are growing and our no's are shrinking. So it seems then that we are hopefully viewing teaching as a more prestigious career than maybe we did before. So that is the end of this lesson, and that is the end of your study of statistics. So as you work through this, as always, ask me whatever questions you have.